one important property of a vector space is its dimension. Today we're going to learn the definition of dimension and discover an important theorem about how to use the dimension of a space to build a basis for the space. All right, so from your reading, who remembers the definition of the dimension of a vector space? That's the definition of a vector space, but just the dimension of a vector space. The dimension is, yes, number of vectors in the basis. So you find a basis, we know how to do that. You just count the number of vectors in there, that's its dimension. So here I've got a vector space V. I want to find a basis, count the number of vectors in it, and give the dimension. All right, so V is the set of all vectors that look like 2a plus c, b plus d, a minus c, and b plus 3c, where a, b, c, and d are elements from the real numbers. So I'm just going to rewrite V sort of in parametric vector form. So I'm going to have a vector for each parameter, a, b, c, and d. All right, so this, my first vector is going to be my a coefficient. So I've got 2, 0, 1, 0. My next vector is my b coefficient. So I've got 0, 1, 0, 1. And then my c coefficients is going to be 1, 0, negative 1, 3. And my d coefficients are 0, 1, 0, 0. That's what. Oh, okay, thanks. All right. So those vectors, now that I've written it in parametric vector form, those are they're definitely a spanning set because that's the definition of span, right? I've put some weights on those 4 vectors, added them together to build my whole set. So this is the span of, I don't want to rewrite all these, but I guess I will. 2, 0, 1, 0. 0, 1, 0, 0. Okay, I put some dot, dot, dots in there because I didn't have enough space. So the span of those 4 vectors is all of V. That's the definition of span. If these 4 vectors are linearly independent, then I have a basis, right? Because the definition of a basis is just a linearly independent spanning set. So it is a spanning set. Those 4 vectors span V. Can you tell by looking? How could I be sure that they're linearly independent? Row reduce, and we would look for a pivot in each column. So that actually comes out properly. You row reduce, and you do get the identity. I'm just going to write that. Oh, actually, I don't know if you get the identity. I haven't done it out. All right, so yeah, you get I4. So it turns out my vector space V is all of R4, right? It spans R4 and it's linearly independent. So it's linearly independent. It's a spanning set, so it is a basis. How many vectors are in this basis? 4. So the dimension of V is 4. All right, so now I want to find another same question, but for a new vector space. Defining this vector space W to be the set of all vectors A, B, C, D, such that A plus B minus D equals 0. All right, so translate that equation to an augmented matrix, and I get 1, 1, 0, negative 1, 0. It's only one equation, so I only get one line, I only get one row in my matrix. So this is my pivot position, right? So this is my basic variable. The other ones are free. So this says A has to equal negative B plus D, and then B, C, and D are all free. So if I write this in parametric vector form, my solutions, right, the set of all solutions to this equation would look like A, B, C, D equals, I'm going to have 3 vectors here with one of my free variables on each. So A is negative B plus 1D, no C's. And then B, C, and D are all free. So I've got 1, 0, 0, 0, 1, 0, and 0, 0, 1. So I just wrote my solution in parametric vector form. So this is the span of those 3 vectors. Oops. So those 3 vectors form a linearly independent spanning set. This was how we found the null space, remember? Which means that my basis is just those 3 vectors. So it's just another notation. Instead of writing the span, now we write basis. How many vectors are in that basis? 3. So the dimension of W is 3. So there was a theorem from the section when we did null space that said when you do this process for finding a null space of like taking your solution and writing it parametric vector form, that these vectors always end up being linearly independent. Yeah. Yeah. Yep. There would be nothing wrong with doing the check, but we just didn't have to because of the equal 0 part. All right, I've got a 4x4 matrix A here. I want to find a basis for the null space. So we know how to do this, right? So remember that the null space is just the set of all vectors that get mapped to 0, set of all x1, x2, x3, x4, that when you multiply that matrix times it, you get 0, 0, 0, 0. So to find the null space, you augment with 0. In fact, I'm going to do it above to save a little space here. Augment with 0, 0, 0, 0. And you get 1, 0, 0, 0, 4, 0, 0, 0, 0, 1, 0, 0, and 0, 0, 1, 0. So my basic variables are going to be x1, x3, and x4 because I have pivots in those columns. My free variable is x2. So I'm going to write all of these. I would say x1 equals negative 4x2. x3 equals 0. And x4 equals 0. x2 free. So this is my solution set for the set of all things that get mapped to 0. So I'm just going to write it out in parametric vector form. I only have one free variable, so I put it up here as a parameter. And then x1 is negative 4x2. x2 is free, so I put a 1. x3 and x4 are both 0. So this is the spanning set. It's just the one vector. Is that set of vectors linearly independent? Yes, any single vector is always linearly independent. And because we have a theorem about the null space that when you do this process, you always get a linearly independent set. So we have a spanning set that's also linearly independent. So that is the basis. So my basis is just this one vector, negative 4, 1, 0, 0. So there's my basis. And then that means that the dimension of the null space is 1, because there's one vector in there. Is there a shortcut to finding the dimension of the null space of a matrix? What was it in this process that led us to the 1, there being only one vector in the basis? The one free variable, right? So I had one free variable, which meant that I was able to write the solution set as in parametric vector form with just one vector times the free variable, right? So yes, it's the number of free variables. So I could, if I had known that shortcut, I could have stopped right after I row reduced and said, oh, there's one free variable, that's the dimension of the null space. All right, let's look for a basis for the column space of A. If you remember from a few classes ago, the way you find the column space is you identify the pivot columns and you grab them from the original matrix A. So I've got pivot columns 1, 3, and 4. Column 2 is a free variable column. So pivot columns 1, 3, and 4, grab 1, 3, and 4 from the original matrix. That's your basis for the column space. So we already did all the row reducing work, so just write down the answer. 0, 5, 1, 0. Negative 2, 1, 0, 4. And negative 5, 14, 2, 10. So that's my basis for col A. So what's the dimension of col A? 3. There's 3 vectors in there. Its dimension is 3. What would the shortcut have been for answering the dimension question without actually having to write down the basis? The number of pivot columns, yeah. Because that's how many columns you're going to grab to form the basis. What do you notice about the number of pivot columns of A and the number of free variables of A? If you add them together, you get 4, right? And that is the number of columns total in A, right? Every column is either a pivot column or a free variable column. So when you add those together, the dimension of null A and the dimension of col A, you always get the number of columns in A. That gets formalized in the activities. So you'll see it in a minute. All right, last question here. We want to find the dimension of the subspace H of P2 spanned by these 4 quote-unquote vectors. Okay, so this is an interesting thing about your book that can get confusing. It will call things like these vectors without saying quotes, right? But when you look at them, you would go, those aren't vectors. But now that we're talking about vector spaces as a more general term for anything that can act like Rn, now your book starts calling these things vectors. So we've got 4 vectors in the set, Okay. So we're looking at the span, so they're a spanning set because that's the definition of H, right? We're looking at H is the span of those 4 vectors. So H is the span, just like sort of summarizing what the way they've defined H here. 3t squared plus t, 2t plus 1, 6t squared plus 2t, and 10t plus 5. So that's a spanning set. We've got a spanning set for H. In order to answer the dimension question, I have to have a basis. I have to know how many questions are in the basis. And a basis is a spanning set that's also linearly independent. So how can I determine if these are linearly independent? Yeah, a linear combination of the ones before it, yeah. So did any jump out at you as like being real obvious? One's a linear combination of some others? The first and the third, right? Because the third one is 2 times the first one. So dash that. We don't need that to create the spanning set because I can create that one by just taking 2 times this one. So we get rid of it. We don't need it in the spanning set. Any others jump out? The second and the fourth, right? The second one times 5 gives you the fourth one. So I can get rid of that one because I can build it using the second one. I don't need it in the spanning set. Now I only have 2 left. Is one of them a multiple of the other? No. So now I have a linearly independent spanning set. And so how many elements are in it? 2. So the dimension of H is 2. So I just basically took the spanning set and whittled it down until it was linearly independent. Then I had a basis.